Heat transfer example problem, natural convection for a double pane window. In order to reduce the heat transfer through a window, a double pane window with height of 1.2 meters and width of 1 meter is built with an air gap between the two panes of glass. If the glass panes are at fixed temperatures of 35 degrees Celsius and 20 degrees Celsius, what is the heat loss for a gap spacing of 3 centimeters for part A and 0.8 centimeters for part B? Our first assumption for this problem is steady, two-dimensional flow of air between the window panes. Our second assumption is constant properties. However, note that the density must be changing for natural convection to occur, but that we use a density at the mean temperature for our calculations. Our third assumption is that there is negligible radiation. This is a reasonable assumption for moderate temperatures combined with significant convection. Our fourth assumption is that we can model the window as a vertical cavity with uniform vertical surface temperatures and insulated ends, where the Nusselt number correlations are reasonably accurate. Our fifth assumption is that conduction will be one-dimensional if advection does not occur. Our sixth assumption is that the air is an ideal gas at atmospheric pressure, which will be used to look up properties. Clearly, these are some significant assumptions, and we should only expect an accuracy of about plus or minus 20% for our results. For part A, to calculate the heat transfer rate, we will use Newton's law of cooling if advection occurs. To determine if this is the case, we evaluate the Rayleigh number at the average air temperature of 300 Kelvin. Substituting in values, we get a Rayleigh number of about 37,000. Recall that for vertical cavities, if the Rayleigh number is above 1,000, the buoyancy force will be large enough to overcome friction and natural convection will occur. Next, we look for an average Nusselt number that corresponds to our conditions, where we have a fairly high aspect ratio of 40, and select the one shown. Substituting in values, we get an average Nusselt number of 1.92, an average convection coefficient of 1.68 watts per meter squared Kelvin, and a heat transfer of 30.3 watts. For part B, we again begin by checking for advection by calculating the Rayleigh number at the average air temperature of 300 Kelvin. Substituting in values, we get a Rayleigh number of about 702. Thus, we conclude that the air will remain stationary and the only mode of heat transfer will be conduction, since we are neglecting radiation. Next, we calculate the heat transfer rate using Fourier's law for one-dimensional conduction, where the area used for this calculation is normal to the direction of heat transfer. For steady-state conduction with no internal heat generation, the temperature distribution will be linear and we get the results shown. Note that we could also get this equation by using the thermal resistance analogy for a plane wall. Substituting in values, we get a heat transfer rate of 59.2 watts. Finally, we note that as the spacing between the window panes increases, there is a trade-off due to the resistance due to conduction increasing, while the resistance due to advection decreases. To consider the effect of this trade-off, let us look at a plot of the heat transfer rate versus the window pane spacing. Initially, as the spacing increases, there is conduction only, and the heat transfer rate drops off significantly. Note that the Rayleigh number when advection would begin is indicated by the critical spacing. We see that initially, the advection has negligible impact on the heat transfer rate. Eventually, at about 3 centimeters, the advection does begin to enhance the heat transfer rate, but very slowly. Thus, a spacing of about 2 to 3 centimeters is optimal, but a larger spacing will not result in significantly more heat transfer.